Hello class. In this lesson, we're going to learn how to find segment lengths in circle diagrams of secants or with secants and tangents. This first example, what do you notice about the lengths that they give us? What's the special relationship there? Well, it looks like if you multiply the lengths on the same chord together, we get the same product for either chord, right? 8 times 3 is 24, as is 6 times 4. And this is no coincidence. We can prove this fact. And to prove it, we want to use similar triangles. So let's draw on these triangles here. And the idea behind the proof is that once we have similar triangles, we can write proportion. And once we have this proportion, we can use the cross product to get AB equals CD. So one way to prove that we have similar triangles is by angle-angle. And we know that vertical angles are congruent. So that gets us one pair. And where can we get another pair of congruent angles? Well, angles YXZ and ZWY are inscribed angles, and they have the same intercepted arc, YZ. So we know that these angles are congruent. We could have used the other pair just as well, so lots of options here. And so these triangles are indeed similar by angle-angle. And so now we can write proportion. Right? We know corresponding side lengths are proportional, so A divided by D has to be the same as C divided by B. And then we apply the cross product, and we get what we wanted. AB equals CD. So this gives us the following theorem, exactly what we just proved. So when you have chords intersecting inside a circle, you can multiply the lengths of the segments that compose the two chords, and those products are going to be equal. So why don't you try to apply this theorem in example 3, and then I'll show you my solution. So our lengths on the same chord here are 18 and x, and on the other one are 9 and 16. And here we simplify. And the opposite of multiply by 18 is divide by 18, so 144 divided by 18 is 8. Okay, here's a different diagram. Here we have secants that intersect outside the circle on the exterior. And you notice a relationship amongst the lengths here. I gave you hints. Figure out how long the secant segments are as well. Well, if we find the lengths of the secant segments, we get 10 and 12. What do you notice now? Well, if we multiply the secant segment length times the exterior segment length, or external segment length, we get the same product, right? 6 times 10 is 60. 5 times 12 is 60 as well. And we could also prove this fact with similar triangles. We're going to, for the sake of brevity, we're just going to state the theorem though. So here's exactly what we just saw in the previous example. So we multiply EA times EB. That's going to be the same as EC times ED. So external times the secant is equal to external times the secant for the other one. So why don't you try to apply that theorem in example 5, and then I'll show you my solution. So let's see, the external is RQ over here, multiplied by RP, the whole secant. We'll multiply RS times RT. So now we substitute. We have 4 times quantity 4 plus 5, which is 9, and 3 times the quantity x plus 3. So we simplify this over here, and we get 36, and we distribute over here, we get 3x plus 9. So you subtract 9 from both sides, and divide by 3, and we get 9. And in example 6, what relationship do you see here? Well, if we figure out the length of the secant segment here, it's 18. And if we multiply 18 times 8, like we did previously, the external times the secant segment length, that gets us 144. But 12 squared is 144. And that is our special relationship. So we have a secant and a tangent. We're going to still multiply the external segment length times the secant segment length, but then we're going to square the tangent because the tangent doesn't have any part on the interior, right? It only touches the circle, exactly 1 point. So why don't you try to apply that theorem here, and then I'll show you my solution. So we know that the tangent squared is going to be equal to the external segment times the whole secant segment length. Say 7 squared is 49, distribute the 5, subtract 25 from both sides, and divide by 5 to cancel that factor of 5, and we get 4.8. In this lesson, we learned how to find missing segment lengths in circle diagrams with secants or with secants and tangents. Thank you for watching this video.